Okay, my name is Estíbaliz Gómez de Mariscal. You can just call me Esti. I think it is easier for all of you. I work at Universidad Mariscal de Madrid. I'm doing my PhD on cell segmentation and tracking, but my background is really from mathematics. And well, that's why I'm presenting today a very basic knowledge about the statistics and then a very advanced topic on how to do a statistical test. And well, I hope you really enjoy it, because for me it's a work that took us some time to do it, and I think it's quite important if you are going to analyze the data you have from your image processing analysis and so on. Yesterday someone said that Spanish people, we talk very fast. So if I do it, because I'm not the exception, please stop me. I mean, I really want you to understand what I'm presenting to you here. So yeah, just raise your hand and ask whatever. So the idea is that I'm going to introduce these concepts that most of them probably sound familiar to you. Then we're going to do a 5 minutes break so you can clean your mind, and we will come back to treat this work about how to use the p-value as a size-dependent function. So you usually, when you do measurements, it is a process of experimentally obtaining the value of a quantity. So you know that there's a theoretical value, but you don't have the analytical formula to get it. So you do some experiments in order to approximate this value or to get it. And the idea is to get the optimal measurement procedure to be as close as possible to the true value. So what does this mean? We have a quantity, and we have the true value and the one we measure. The difference between these two is called error. You all know this, right? And the value we get from the experimental measurements and all the range of values we can get, like the standard deviation, is called uncertainty range. So what is the difference between these two? The error is something that we cannot really measure, because usually we don't have our what's going on?
That's the error.
That's the error, yes.
We'll go on.
I can use this one as well. Use the cable. Okay.
Yeah.
Where is this one coming from? Oof.
Very unstable.
Yeah, maybe some cables are...
The cables.
I think because when we touch
Yeah,
this...
we touch a little bit over there.
Is it connected? No.
It works. For now.
Don't move for 1 hour and a half.
Don't breathe.
Okay, so... No, is there something here maybe?
This is a... This is this sound.
But for instance, you can see it here.
Yeah.
I can use the VGA as well.
Yeah, but I won't be able to capture it.
Ah.
Otherwise, what kind of resolution are you using?
That most of you know this measure is the variability or dispersion of the data with respect to the mean, and it has this formula. We are not going through equations, it's just You can have it there. The next one is the standard error of the mean. That is how far is the sample from the estimated mean. Okay, it can be used as a value of how accurate is your estimation, and many people like it. And the last one is the confidence interval, and it's a range of values. It can be 90%, 95% confident that it contains the true mean value. We will see later on what happens with this. There are different ways of calculating the confidence interval. If you know the true variance, you can use this formula. If you don't know it, but your n is large, you can use this other one, and so on. Usually, in your software, it is already incorporated all this information, and I'm sure that many of you, you know it. You don't know it? Does it sound like really unfamiliar for you? No? Okay. So, visually, what is the difference between all of them? If this is our sample, and this is the mean value we are calculating, the standard deviation is usually the widest one, okay? And that is why this value is quite interesting, and is the one that statisticians most like. The standard error is usually very small, and the confidence interval, it gets larger and larger as long as we increase the level of confidence we want to get in our measure. But what happens with this confidence interval that you usually need to report it with your result? If this is our population and we get some experimental data and we calculate for different instances of data the confidence interval, not all of them are going to contain the value we want, the value we are interested in. Okay, that's why we need sampling. So the first definition of the confidence interval, and the one that you usually use, is false. Okay, what it means is that for each 100 intervals that you calculate, only 95 of them are going to have the true value. So you cannot only calculate one confidence interval when you have your data, but many of them, and then you average them. Okay, because they vary. They are not fixed measures. What else we need to take into account? Or how do we do it? We have our population, and we take one sample, and we calculate the sample standard deviation and the sample mean of all the samples we get. The true thing is that any finite sample of the variable will have a different sample mean and standard deviation. This is what we already saw here. The second thing is that we need to repeat the sampling and calculate a mean each time we do this sampling. And how do we what do we get at the end? So let's say that this is what we wanted to estimate. We do our sampling, and usually what we get is a thinner distribution of the data. What we get here is our mean value, the one we wanted to calculate, and this is the standard deviation. So the resulting means will be distributed according to the sampling distribution of the mean. Do you do samplings when you calculate any quantity or anything? No. Yes? No? Cross-validation? How many of you? Yes? Good. Okay. So this is something that I discovered when I started working with biologists and so on, that you usually have your data, you report on your value, and that's it. That's wrong. You should never do that. How can you solve this? So this is your data. Okay? And what you do is you fix an n value. I'm going to take 20 samples each time. And I'm going to calculate for each of these groups a mean value. And what I'm going to report is not the mean value of all these data sets. What I'm going to report is the sampling distribution of each of these groups. I'm going to calculate the standard error of these values, because these ones are the ones that are going to give us the most or the closest estimation of the value we really want to get. Okay, and this is what is called sampling statistics, and how you get the confidence intervals and so on. For this, and if you want to calculate the confidence interval of these values, the requirements or conditions you need to fulfill is that this sampling has to be randomly chosen. Okay, they cannot be correlated. You can use the random method in any of your softwares. You can only calculate confidence intervals if the data is normally distributed. But the good thing is that you usually calculate mean values. And the mean, the distribution of the mean is always a normal distribution because of the central limit theorem. So this one is okay. You can always provide confidence interval for your means. And the sampling has to be independent. Usually you can do it by using replacement. So you take these points, then you let them go back to the data, and you take another random point, and so on. Sometimes in your experiments, it's not easy to do this, because once you have recorded some data, you have already done your experiment, and you need to repeat the experiment. So that would be without replacement. But in that case, what you really need to take into account is that all the experiments are kind of random, like all the conditions are the same, and you are really measuring something that is not biased. Okay? So now we are going to move to a topic I most like. How robust do you think are these measures? Standard error and confidence interval. And what is the main problem with them? How many of you have reported confidence intervals in your research works? No one? No? You have never worked with confidence intervals? No? How many of you have to, I don't know, I'm not a biologist, but to report whether a drug is working or not? No. Yes? So you have never done statistics?
I see some saying yes. So. I usually report like standard deviation or standard error.
Yeah.
The standard error.
Yeah.
Okay. What is the problem with the standard error? Do you think it is always the same? Why not?
Like, it depends on the sample size.
It depends on the sample size.
Yeah, and in my data set, like also when I'm doing like checking for p-values, it's kind of cheating because my data set is like huge. So obviously my p-value is going to be.
Okay, so we are going to address that problem specifically. Okay, so all these measures, they depend on the sample size. So if you change your sample size, you can change them. It's very easy. If you have a very big sample size, your true value is very well estimated, and your difference are going to be evident always. But that's kind of cheating, as, sorry, your name was? Daniela, as Daniela said, because you can, if you have a lot of money, you can keep recording data until you get whatever you want, okay? And that's what it happens with these measures. So, for example, here we have different distributions, and what they do is they do this sampling, they calculate many mean values for different sizes of n. So remember here, the groups can be larger or smaller. And what they get is, as long as they increase this value of n, the distribution of this mean value is thinner and thinner and thinner and thinner. Okay? So what happens is that the true value is very well estimated. But if we want to compare this one with another data set, there we can have many problems. Also, if we look at the confidence intervals, if the n is very small, the confidence interval is very large. We have a lot of uncertainty, so we cannot know where is the 95% of our confidence, so we need a very wide range of values. If our n is very high, the confidence interval and the standard error are very small. And this is a very common way of cheating in your data, and of cheating when you are doing visualization. So whenever you see error bars, just think about the size of the data and how did the people who did this work, how did they get them. So, to keep on, what we can see is like, if we take 3 different samples coming from the same distribution, and we calculate the sample mean for each value of n, and the sample standard deviation and the standard error, we can see that there is a relationship. We can see that there is indeed an n value where the 3 samples, they converge to the true value. And what you could be interested in is, okay, what is the sample size I would really need to record in order to get my true value well estimated? Because sometimes you don't want to compare between two conditions, but just to estimate well whatever you are measuring, okay? Temperature, speed, or whatever. So for this, it is true that there are certain formulas you can use to get this value. And actually, these formulas only work if you know some parameters, like the standard deviation of the true population. Like maybe you don't know where is the mean, but from previous studies, you can know how varies the measure you are going to study, right? Like usually when you do some research, you have read previous works, and you should have read previous works, and you should have, I don't know, get some of their values in order to plan your experiment and plan your analysis. So this value is quite important, or you can always ask to the expert, what is this value? As our professors used to say, you can ask to the expert always. You need to know what is the confidence level you want to get, okay? How precise you want to be, and the error range or the length of this confidence interval. And with that, there are different formulas that you can use based on the fact that the distribution of the mean value is a normal distribution. Okay, if it is not normal, you should do something more complicated, but we are not going to approach it now because usually you always calculate the normal value, okay? The mean value, sorry. But you can use these formulas to get what is this precise M value that is going to give you the convergence heat, okay? So these calculations are very common. I know in pharma companies, in medical experiments, and when you need to calculate the number of patients you need to analyze, or the number of rats you need to sacrifice, and so on, okay? So it's quite common. Here I let you just for, if you go back to the slides, you can have all the formulas depending on the experiment you want to do. And I think this is all right now, and then we are going to move to p-values that I thought you already know them, but I'm not very participative. So just 5 minutes break if you have questions. No? 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 Yes?
So what if, like, you're not really sure about, or there isn't much data about what the variation is supposed to be, or what the previous experiments, like you don't have much information.
If you don't have much information.
Yeah.
Okay.
Can you repeat what he asked? Can you repeat what he asked?
Okay, he asked, if you don't have information about your experiment, you don't know the variance, you don't know anything, like you want to be super innovative and do something super new, okay? Right? Okay, there are different ways of doing it, okay? If you are taking a Bayesian approach, because it's true that you don't know the variance, but you should have some knowledge about, what's going on in the field. Usually when you do a work, you want to approach this point, but you go slowly. So if you know something, you can use Bayesian statistics in which you incorporate some, you hypothesize that your data is going to follow a certain distribution, and then you keep on, you compare with this certain distribution, and if it is well approximated, good. If it is not, then you try with another one, or as you already have some data, you can work with that. Actually, the work I'm going to present now, it's more or less about that. Like you can say, okay, right now I'm going to do 20 experiments, okay? And when you have your 20 experiments, you analyze your data. And you say, okay, I think I need more because this is really unbiased, or if it is something really handy, you really need to repeat it because there's a lot of error on that. And you should kind of target, what you are getting. Actually, these values here, they are going to tell you when you are going to have statistical significance but they are not going to tell you whether that significance is true or not. Okay, like maybe there is some effect in your data that you can discard it. So even if you get like, let's say you are measuring the weight of people, okay? If you are saying one population has weight of 63.5 kilograms and the other population 63.8 kilograms, okay, maybe you have a statistical significance. You will probably need to have an M value of 10,000, but it is not something that is important, you can discard it. So I will move into Bayesian statistics, or I will try to find a way to determine this value here. Okay, maybe you can measure, I don't know, the variance of your components in the experiment, and that will give you an approximation. Okay. Questions? Any more questions? No?
Just maybe, what about the expertise of the biologists? You were talking about weight. We know that 0.3 and 0.8, it's really small differences. Can we also use this?
You can measure, you mean like use the expertise, I mean if the biologists know that is insignificant, use
yeah, for instance, you're measuring two length of, I don't know, microtubules, for instance, or cytoskeleton components, and you know that it doesn't make sense to look at a difference in length of that is smaller than, I don't know, a few microns or a few nanometers. I know, so.
Yeah, so you can use that here, for example, when you describe the length of your confidence interval, because you can say, okay, I don't want it to be between 10 nanometers and 5, because that's quite a lot, and I don't want it to be super small, because then I don't give enough space. So you can use it there, and you can you can calculate the effect size, which is just the difference between two mean values divided by the standard deviation. And you can use that value to know whether it is like the difference between your samples is very high or not. For other kind of experiments, like you're analyzing when an event is happening, you can use the odds ratio. I have the measures later for like at the end of the presentation, or correlations, or I mean, you should always provide a lot of data descriptors. Okay, so the reviewer and anyone can understand what you are doing. But yeah, effect sizes and the length of the interval will be a good way to measure that. Yes?
Do you have like maybe advices about when we start designing our experiment? And maybe when we do sampling and so on, what like things we should like?
Sampling or deciding how many experiments you want to do?
Yeah, first maybe designing how many experiments.
It's a good question. I mean, I would use this.
Yeah.
Okay. But I would try to calculate it with different sigma values, for example. And I will try to measure also what's going to be the error in your measurement procedure, because that is like, one thing is this number, and another thing is how able you are to get data properly. And those errors are not here. So maybe you could first measure the uncertainty in your devices, or how many people is going to be doing the experiment and what is the bias between these people, and then try to integrate it in this value here. And then calculate the M value using these formulas. Yeah. I mean, if you don't know sigma, you can always, if you have previous data, use the estimated variance or the quasi-variance and try to use it. I mean, there's not a strict rule for that, because you're going to do something new that you don't know anything about that before. So if you knew beforehand everything, you wouldn't be doing this experiment, probably, right? Okay, so let's move on. Now comes the fun. Okay. So, this is a work that we recently uploaded to bioRxiv. It's a bit controversial because I'm just saying that p-values are useless as in the way they are being used, and I really want you to learn this, and I really want you to go out from this room with this idea in mind. Okay, then you can do whatever you want, but please, if you don't understand, we will be here for hours, because I do really want you to understand it, okay? The thing with p-values and statistics, and I think what is going on is that in the recent years we have been able to record a lot of data. So we are discovering some behaviors in statistics that we didn't know before, okay? And that's why there are many papers, actually there's a whole section in Nature Methods called Points of Significance dedicated to this fact, okay? About how to use error bars, what is going on with the significance, what is the impact of criticism of null hypothesis significance testing on statistical reporting practices in conservation biology and so on. And they are trying to teach the people how to use the statistics, okay, and what they are doing. But at the same time, there's a lot of people who really want you to not use statistical significance, to stop using binary decisions and learn how to work with uncertainty. I would really recommend to read this paper because it's actually very nice. This guy from Stanford University, he just took many research works in neuroscience and he proved that all the results that they were reporting were false. That they just were reporting p-values smaller than 0.05 because they needed to publish their results. And that is the fact. You need to publish, so you need a statistical significance. If you don't get it, someone will ask you, hey, you don't have p-values more than 0.05, you did nothing, okay? So this, what I want to show you is between these two, okay? I know that it's very difficult to work with uncertainty, so let's try to move one step to leave this comfort area and be in the middle, okay? And then we can move to work with uncertainty. Well, this is the index we will follow. And what's happening? So, this kind of a statement is true. Extremists see the world in black and white. Political moderates saw shades of gray more accurately than did either left-wing or right-wing extremists. Do you know it is? Do you think it is true? It can be, no? Okay, so these guys, they did this research and they put people trying to distinguish the gray shades of some letters, and the conclusion they got is that the extremists were not able to distinguish accurately the shadows and the gray levels, okay? They were only black and white, and they published their work. What happens is that the reviewers, they told them, this is a bit weird. Can you repeat the experiment, please, and report again your data? And when they repeat it, it was false. Okay, they got a completely different p-value. So it's quite funny, right? Another thing we can see, especially in my field, is our method improves 9% the accuracy of the state-of-the-art method. It has an accuracy of 85% against 78. I say, wow, this is a very good method. And the true thing is that there is no any kind of improvement and there is no kind of relationship between the way you see the grades. So both distributions are very similar, but people have a lot of data of the perfect combination of data and they get this magic p-value lower than 0.05, okay? So we want to avoid this, and you are going to avoid it from now on, okay? So now, what is the p-value? Come on.
Probability that your observations occurred by chance.
That your observation is done by chance. Under some condition.
The probability that you'd observe that in the null, by chance, if the null hypothesis is true.
Exactly. If the null hypothesis is true, what is the probability of getting the data point? If the probability is very low, then there's I mean, the data is by chance and the null hypothesis is false, okay? That's the p-value. So for the common students t-test, what you have is two distributions, and you hypothesize that the means of both distributions are equal. Then what you do is you calculate the difference, the weighted difference, and you get a t statistic that you compare it with the normal distribution, and it gives you this p-value. The probability that we would observe a result as extreme or more than our result if H0 is true. So if my mean values are true, what is are the same, sorry, what is the probability of getting the data I reported? Yeah? So if this p-value is very small, then either H0 is not true, or either we observe a low probability event. Okay, so H0 is not true. So, do we always get this value, or when do we get this value? So we are going to make an experiment. Let's simulate two normal distributions, okay? One with 0 mean value, and the other one with 0.01, and one standard deviation. And we are going to compare them. We compare them using different sample sizes. So here they look very different. Here they started looking similar, but all these p-values are completely different. And actually, this one is telling us that both distributions are different. Do you see the difference between them? Because I don't. No? And in this one, they are telling us that they are different. And we know that they are almost the same. It's just that we have very low data. So p-value changes, okay? This means that this p-value, as they are a variable, they have a distribution. So what we did is, okay, we are going to calculate many p-values for different sample sizes, and we are going to compare different normal distributions. Here the distributions are the same, like exactly the same. We sample from these normal distributions, and we see not only that the p-value is not always the same, but also that is completely random, and it can give us a value very low, so we could be having false conclusions, and a p-value very high. We keep on doing that for another normal distribution with mean value 0.01, with mean value 0.1, and we keep on, and we can see that as long as we get farther from this normal distribution with mean value 0, our p-values started to decrease, which is what we expected. But they kind of follow some distribution that seems to be able to model it, okay? So if we look at this, we can say, okay, this maybe follows a function, and this one can be just a straight line. So what we did is, okay, let's take the mean value of each of these distributions at different sample sizes, and let's analyze it. Thus, we took like a smooth function, we did it with many points, and we tried to fit a curve. Does this curve sound familiar to you? You smile, why? Do you know the answer? To the what?
That's, I don't know.
So I'm asking whether, do you know what function can we use to estimate this smooth curve? Logarithmic? Easier one. The exponential. Right, it is exactly as an exponential function, and the exponential function is really great in mathematics because you can derivate it, integrate it, and work with it. So it looks like an exponential function, and this was nice, and actually this is not new, okay? So we know that for the statistical t-test, the p-value can be approximated by an exponential function. It's known for many years ago, but still everybody reports a p-value. So it's kind of like, what the hell are you doing? You know that it follows a function and you are still trusting all these p-values, even in I don't know, drugs or whatever. So we fitted this exponential function to all the comparisons we made before, and it fits perfectly well. We can calculate what is A and what is C, and get a very perfect fit, because this difference is very small. We measured it and it's insignificant. And then we say, okay, so we have this exponential function. We know that the p-value depends on n. So what is the connection with p-hacking? What is p-hacking? Do you know what is p-hacking?
Sorry, one question before. And did you check the same thing with the median?
So actually, the smooth curve is fitted only to the mean values, and the exponential is fitted using the entire data set. Not the median or the mean value, but the whole points here. So you account for, that's why also you have this difference here, because the mean value is a little bit higher. So if you use the entire data set of all the estimated values here, you get, you account for their bias. Any more questions here? Yes?
How do you say it's insignificant difference?
Because we measured the conclusions you get using the method are the same. This is not a curve. This is just like a connection of all the mean values. So your mean can always be biased. It's better to use the median, as Matthew asked. So actually, we know that this is okay, but this shouldn't be the true function. And then if you look at the literature, you know that for the t-test, there are many papers about numerical approximations that you can approximate this function with an exponential with almost no error. So we know that for one case it is true. We tested for different statistical tests, and for all of them we get the same. So we assume it is true. Of course, we didn't prove the analytical expression, because that would be crazy to do it with probabilities. But there are evidences in papers from 30 years ago, which is, so yeah, we can say, and there are works that support this conclusion as well. So, yeah, what is p-hacking? Yeah?
Do enough experiments and then
To hack.
enough samples size, higher sample size you get.
Can you speak up, please?
Oh, sorry, I was saying you do enough experiments or you increase, you get to a point where, the p-values will be small enough.
Exactly. So many people, when they are doing their experiments, they are calculating p-values all the time until they get the one they like, and that one is the one they report, and that is called p-hacking. Okay, and it's a whole phenomenon. We are not going to discuss about it, but we are going to, there's one reason why you can do p-hacking. So what is the connection between what I explained to you and this?
With higher number of samples, your p-value decreases.
Exactly. So you have a function of n, so you will be always able to hack your p-value, like always. Even if there's this case here, because these follow uniform distribution, so you will always find something here that is going to support the conclusion you want, but not the true conclusion. So, under the same conditions, the p-value is different depending on the size of the sample, so it is possible to get the desired p-value with a large enough data set. So with this, we got our new model, which is an exponential function, and we just need to know what is A and what is C. And the next thing is that when we fit this nice function, and we plot how C changes with the mean value of the normal distribution that we are comparing, we see that there is a relation. So actually, this parameter tells us what is the decay of the exponential function. So we can see that the larger the difference is with our distribution, the larger the decay is. So we start to see how to characterize the data with some kind of fixed parameters, okay? So yeah.
Just to be sure, the black point of the marker is behind the red.
No, so you compare the black with this one, and you get, yeah, it is behind, sorry. And then I mean, it is 0 because it's this case, there is no decay. And you compare this one with this one with this, and with the other one, and as long as the black one is more different from the ones here, the decay is higher until you get like a straight line here. So the significance is kind of related with this decay. But now you say, okay, this is super good, but as our collaborator said, I want a 0 or a 1. I want to make a decision. I don't like these C's, I don't like this uncertainty. I want you to tell me when I have to say that my drug worked or not. And then we thought, okay, this is the logical procedure we follow. This is our p-value. And this is the statistical significance, right? The confidence level we want to have. So first, well, sorry, I missed this part. So the good thing of having a function is that actually you can already calculate your n value, right? Because you can calculate where is the crossing point between alpha and this chord. And this n value deals with the standard deviation of your data, deals with all the problems because we estimated it. We use cross-validation to calculate it. So this value, we can trust it much better than the previous formulas that I gave you and are the classical ones. So now, yeah, if the data is statistically significant, all the values are going to be here, right? If it is not, our curve is going to decay much slower, and the data is going to be around here, like the p-values. And this is our statistical confidence. So how would you assess the null hypothesis? I mean, what would you do to measure this fact that we have all the values here or all the values below alpha? When you compare two things, what do you do?
So you can compare, because you have a different, is the question about if you have a different number of samples or if the means are very different?
So let's remember why are we doing this. We are comparing data and we want to know whether there's a statistical significance or not. So we estimated the p-value and we have our curve. Okay? And now we want to know in which of these cases there is a statistical significance. But we know that if there is a true statistical significance, the curve is going to decay very, very fast, and all the values are going to be almost here. And if there is not a statistical significance, even if we are going to achieve it at some point when the data is very big, we know that this decay is going to be smaller and smaller and smaller. So how would you compare? At the end, you want to compare it with the confidence level. It can be 0.05 or 0.01 or whatever you want. So how would you compare these values here with this fixed level of confidence?
Would you look at the area under the curve?
Who is speaking?
Sorry, the area under the
sorry.
curve? Do you look at the area under the curve?
And why do you take the area under the curve?
Because, I don't know.
Okay, so which area?
I mean, if you're looking at one particular point, say, if it's, I'm assuming you said you want to look at a specific point, right?
This one, I'm looking to this one. So you will take all this area? No.
I don't know. I think maybe the whole area compared, or would you look at the decay rate?
You can do whatever you want.
I'd say the decay rate, or maybe, because it looks like they're different, the rate is different in both, right?
But the decay is like a number. It's very difficult to know, okay, this is high or low. But yeah, it's kind of the area.
Oh,
so what we do is like, if in the ideal case, it was a statistical significance, everything will be here. But what we have is this. So usually when you compare things, what you do is just the difference between them. So you go point by point and you make the difference between this curve, like this point, and the alpha value, and you subtract, right? Yes, do you see it? So if you subtract each of these points, you subtract this value, what you are doing is the difference between areas. Because you integrate it, we have a continuous function. So comparing Pn with alpha of each value is the same as comparing this red area with this blue area. That's what we do. And, okay, before that. And the thing is that if the blue area is much larger, then it means that this one is super small and we have a statistical significance. Yes?
How did you estimate the p-value curve in the first place? From your data, you have your data?
We will go through that. We do use Monte Carlo cross-validation. Just sample many p-values using some random method, and we get all the distribution. We will go through that.
And so you use the absolute value of the difference?
No, because I'm going to use whether it is negative or positive to decide whether it is significant or not. But before that, there's one problem. Do you think that if I subtract this curve, I subtract it with this one, won't it be always positive if I have values until the infinite? Because this one converges, if you remember here, if I keep doing it like that, this area is going to be always larger. So what we said is, okay, we are only interested in the elbow of the curve, okay, where we have our decay, which is this one. So we are going to do all our calculations in this range. So we measure when is the curve going to converge, which is at this point, and now we are going to compare this area with the red one, or this orange area with the blue one, okay? And if the blue one is bigger, we reject the null hypothesis. We say that there's a statistical significance, and if it is smaller, we say that there is not, because the decay was very, very slow. Do you understand this? Because this is the key point.
Could you repeat that?
Yes. So we have our curve, okay? If we move until the infinite here, and we compare this area under the curve with this blue one, the blue is always going to be larger, because we go until infinity and the blue is going to be constant. So then we need to define, okay, where is the information we are really interested in? And it is here. Okay, so at the elbow point. So we just do our calculations until this point here.
So when you say the elbow point,
The elbow of the curve.
yeah. So okay. So when you say elbow, I thought it would actually be at the probably near the 1,000 mark where it actually. So when you say elbow, I thought it was a point where the most.
Yeah, I mean here, where you have really the change in area of the curve. Okay. But I mean, actually, this is what is telling you whether the curve is decreasing very fast or not. Because if this elbow is almost a straight line, like a corner, then the decay is super fast. If it is smooth, almost like a circle here, then it decreases very, very slowly.
How to calculate the elbow point?
So that is actually a little bit tricky, but it's defined. And you measure the derivative, okay? To measure where is the convergence. As we say, okay, when the derivative is smaller than a parameter gamma, then I arrive to the convergence point. And how do I define this? Okay, so we are using values between 0 and 0.1 for our confidence interval. So this value has to be at least smaller than 0.1. Because, I mean, what do you define as a small? Small has to be related with the range of values you are working with. So it should be at least smaller than what you decided to be statistically significant, which is this parameter. And then there's a relationship like that gamma divided by C has to be smaller than alpha, because otherwise you are measuring a huge value and your A, I mean, there's a whole proof of that if this condition is not satisfied, then your exponential will be like uniform, so you can really like limit the range of value of gamma. Yes? Any question with gamma? Yes?
No, so, so you're saying that if the rate of change of the p-value, in that case, you're trying to say it has to be smaller than a certain, let's say gamma in this case, and then that's when you say that's the elbow point.
Yes.
And but I didn't get the gamma bit. Like what exactly?
The
how
gamma.
you, how you determine that like point?
Okay, this gamma is okay. So the derivative is how you change point by point in your function. So gamma is telling you what you consider to be no change, because the elbow you calculate at the point where you decide that the function has not changed, like it is a straight line. So it won't be zero always, especially because well, it can be zero, but it's an exponential function. So to be zero, either a is zero or n is infinite. I mean, yeah, the function equals zero is in the limit, or only when a is zero. So then you need to define a threshold, okay? And this threshold, it has to be small. And small, in this case, means something similar to alpha, because it's what you are using to measure your statistical significance. On the other side, if this condition is not satisfied, then these all values will be larger than alpha. I mean, if you derivate this and you do you solve the equation, you get this constraint. Okay, so you know that these two things have to be satisfied, and that gives you a very short range of values for gamma. And then we did like the whole experiment of robustness with this parameter, and there's one value of gamma that works perfectly with the experiments and with the theoretical data. So we really limited it. And if you change it a bit, the result doesn't change that much. So that's the good thing of this one, and that was very surprising, actually. Okay.
So just one thing, the difference between, so to get the p-value curve, you need to get hypothesis on the normal distribution.
Actually, if you're not using normal distributions, you can use Mann-Whitney test, or you can use non-parametrical test. So your distribution can be not normal, can be whatever.
Okay.
You can have different distributions. Actually, with the experiments, there are not normal distributions with the real experiments, and everything worked super well. So yeah, you can do with any statistical test you want. I use normal distributions because it's easier to understand and to see things, but we will see later. So, okay, so we define this difference, and with this difference is larger than zero, we reject the null hypothesis. And we try it with our normal data, and what we get is that we reject the null hypothesis for these cases, and for these ones we cannot reject it, which is the same as saying, okay, we consider these normal distributions with respect to the 0, 1, 1 to be the same, which actually they look the same. I will never say they are different. And these ones to be different. Okay? Yes?
What if your sample size is so small that the p-value is not convergent? This p-value curve.
Yeah, I mean, for a small, what I will tell you is that with a small data, you cannot make any conclusion. I mean, yeah, I mean that's what I will tell you. And what is small? If small is 100, you can do something. If small is 10, I mean, I wouldn't trust that research. We will see what happens with the small data.
In reality, I don't know how it works for other people in the reality of biological research. It's never so large.
With bioimage analysis?
Yeah, in the it's mostly cell biologists that work in my institute, and I didn't see large numbers of.
Yeah, because you
experiments.
cannot repeat many experiments, right?
Exactly. Yeah.
I mean, that's.
I mean, they do exactly well. They do p-values, right? That's what they do.
I mean, in that case, what you can do is cross-validation, and
Yep.
you can provide a deviation of your p-value, for example. Yes.
Yeah, maybe related to this, what exactly do you consider sample size? Like, I mean, for example, you have from one day a lot of microscopy images with many cells, but then maybe you have a second well from the same day, and then you have repeated the experiment on another day with another sample. So what is sample size? And is it the cells you imaged on one day, the cells you imaged on all the wells, the cells you imaged ever?
That, if you are measuring how the skin grows, okay, let's say you are doing some bioprinting or something, I don't know, and you have different places where you are growing skin, your sample size will be each of these different independent places, okay, so you need them to be independent. So that would be each of the experiments. Different days, it really depends on what you're measuring. So in my case, I was measuring cell migration, and of course all the experiments were done in different days, but they were done in different plates and in different wheels and so on. So I took each of my cells as an independent point. In that case, it's really experiment dependent. If you want to measure how well something happens under a certain condition, then each of these conditions can be your end value. It's something. I mean, I cannot know if I don't know the problem. It depends on what you're measuring. Yeah. Yes.
So what if from theory we know that two distributions are different? Like for example, we have the first red.
Like this one, right?
Yeah, any of the red, which we rejected right now, the empty circles.
Okay,
so what if we know from theory they are different?
If you knew from theory.
Yeah.
But if you knew from theory, why would you be doing this? I don't understand the point.
Make an experiment to test it. But basically the question is how precise is cutoff method? What if I knew from some theoretical conclusions that one of the first four distributions, they are different. They're not the same as the black one.
I mean, if from theory you get that this is different, I don't know, something. I mean, they completely overlap. They are indistinguishable. So I know that the tricky point, it might be here. When these differences are really important for your experiment. Like let's say, I don't know, you're doing some physical experiment and really a slightly difference is hard. Then you could increase the gamma value, you could do it like stronger, or you could decrease the alpha value, the statistical level. And you could also measure the effect size, like how big is the difference between this mean value and this one. I mean, in that case, okay, maybe this difference is huge, but the overlap between both distributions is also huge. So if you try to know whether in reality it makes a difference, I would say that you could even not notice it, because, I mean, if maybe the system is a bit chaotic, yes, but if not, the two conditions are almost the same. So, yeah, I don't know. I mean, if you know from theory, probably the differences are much larger than these ones, like things are more evident. Yes, no? Okay.
You did lose me a little bit there, because it's a simulation, right? So the orange ones, you say they overlap, but your simulation is two distributions that are different. Okay, the difference is only 1/10 of the standard deviation in the mean, so it's a very small difference, but you're now saying that they are not different, and then I get a bit confused.
No, these...
Your method doesn't show them to be different anymore, which is okay, if your simulation is of two different.
Yeah, but the thing is, okay, so here is the I know that you are saying these are two different normal distributions, right? Because you put a different mean value.
Yeah.
Yeah. So the point here is that we are not discussing whether the mean value is different. This method is more when you have to make a conclusion and you get this data. And if you are trying to say, like, hey, the data that I treat with my drug makes really a difference.
For drugs, not for physics. I mean, if you have very good control of your measurements, and you can repeat the measurement millions and millions of times, you could get a very high confidence that these two distributions are different. You could measure the difference.
But then they weren't look like that.
But they could, if there is noise, but the noise is very well controlled, and it's always normally distributed.
Okay, but I mean, if you have control, and this is not when you have control of everything and you can really say, like, I'm able to distinguish. It's more when you are doing an experiment where you cannot control and you need to provide evidence or you need to make a conclusion. So for physics, it's true that I got a lot of rejection of these things because, I mean, I don't know if you are a physicist or not. You are, okay. So many of you tell, like, hey, there are cases in which here I have differences. Okay, but it only happens in physics. Like where you have everything theoretically super controlled, the experiments are super nice, but...
Yeah, the point is, if you need to know how big the biological noise is. If you know how big your biological noise is.
That's the issue. I mean, we can control it as much as we want, but every day there's going to be something really different.
Yeah, I mean, you are working with a life experiment.
But the point is not yet made, I think, because you now say the biological noise is something that I can maximize. These ones are significant, and this side they're not. But that depends a lot on the type of experiment that you're doing, right? How well you control your noise.
Yeah, of course. I mean, if you can control everything, I mean, if you can control the noise, you can remove the noise as well. No?
Well, no.
If you can model the noise, you can remove it from the distribution.
Would be nice.
You can remove it.
Wait. You can
Anyone from signal theory here?
You can deconvolve your signal.
Yeah. So then you could solve this situation.
For example, I'm doing now biology, and I a lot of noise and a lot of messy experiments, basically. And I like the thing with the p-value decay, and I would then report the way that the p-value decays with the sample size, because that tells you something about how noisy it is. But I would stop there. I would not try to make an arbitrary decision. This is the
because you know how to work with uncertainty, and it's what I said at the beginning. Working with uncertainty is the right way, is where the light is. But we can, I mean, you can work with that, I can work with that, but people who need to make a decision, or people who is not confident with statistical methods and uncertainty, they want something that supports their decisions, that supports their research. So actually, this is because a biologist told us that I need a 0 or a 1.
Yeah, but then how do you defend this choice of 0 or 1? That's still not clear to me, because you just said it basically big hand waving to me. These look the same, the other ones look different.
Okay, I will measure the effect sizes first to know whether the difference I'm measuring, I mean, is what Marion asked, like whether the difference I'm measuring is really important in my experiment. And then I will do this. And of course, instead of reporting the 0 or 1, I will report my curves and these coefficients to show how the data changes. I wouldn't use a 0 or 1, but you know, people need to provide a 0 or 1 to support their conclusions.
Yeah.
So that's, yeah. So yes?
I mean, sometimes when, for instance, we have two models to compare, and we have two models, for instance, to compare, looking to the effect, and we used to use like AIC, like criterion or p-code.
Yes.
Are they like more relevant than a p-value, or?
I mean, it's not more or less, it's another measure. The problem with AIC is that it doesn't have a limited range.
Yeah.
So what is high, what is low?
Yeah, I mean, just
That is used to compare models. Like I have one model, I have the other one, and then it's super good because you know that one has a larger AAC than the other one.
So it's a comparative method.
It's more a comparative method within models. But if you just want to know whether if you have this data, you are not comparing to models, you are comparing to distributions. So it's a bit different. If you are able to model both, then yes, of course. Yes? No? Okay. So yeah, let's move to the use cases. So the way, yes?
One last question.
Yes.
Wasn't, you can go to slide 36. Is this difference not highly correlated with the derivative of the decay?
The derivative of the decay, which difference? This?
Yeah. The
Um,
higher the derivative, the more likely the difference is.
the higher the derivative, the most likely it is delta positive is. Yes.
So we
Yeah.
measure the derivative.
How do you measure the derivative?
No, if you could just measure the derivative and take the definition
You can measure the derivative. I didn't try, but then I get a value again, and yeah, because what do you mean to analyze the derivative of the entire function?
or just the other.
But the ego changes with n, like it's a continuous function.
Yeah. So you get the point of maximum magnitude and then you decide based on I don't know. Thinking out loud.
Okay, I will try that. I will tell you later why it doesn't work. Yes.
One short question. Can you go to the slide before the use cases? There is a colorful. Yeah, this one. So the whole point of this approach is to get away from the number of samples.
Kind of, yes. Is to analyze your sample to be able to characterize using measures that you know what they mean, as p-value, sample size, statistical significance, and to use the fact that you have many points and you have do cross-validation to see how is the behavior of your data as long as you increase the data size.
So are you going to modulate this curve to the number of sequences and show us that the empty circles stay the same all the time?
To model which curve?
So by changing the number of the sample size,
Yes.
could you test? Could you test that the empty circles they are always the same? So if the point of this approach is to get away from the number of the samples, then whatever the number of the samples you have, this curve, the empty circles on the left, they should stay all the time the same.
Yes, because they are uniformly distributed. Yes. So for these cases, where C is 0, your p-value is just it follows a uniform distribution. So in that case, you can get away from the sample size, plot the distribution of the p-value, and see that it is uniform, that it doesn't have any shape. Actually, if you plot I'm not going there, but like the distribution of all p-values without taking care of the sample size, you will see that the distribution is just, it has this shape. Like when there's a very high statistical significance, it's like a very sharpy exponential function. But the problem is that you could analyze that distribution and say, okay, if it is similar to one model distribution, then I reject the null hypothesis, and if not, no. The problem with that is that you are not able to analyze how this p-value changes as long as you change the sample size. And this is an important fact, not only because it is telling you that you can hack it, which is one of the main points of this, but also because you can know like when is this difference happening. And that value is very useful for a future person that is going to repeat your experiment, for example. And it's easier to understand, and actually when you analyze the distribution of the p-value and you try to make a model to ignore the null hypothesis, it is less robust than if you use this. Because here you want a very high decay, you want a specific M value and many things that you know that they have to be like that. But yeah, when there is no difference, you can take just the distribution and everything will look uniform. So how to use this? Yeah, the way we do it is we estimate the distributions of p-values using Monte Carlo cross-validation. So do you know what is cross-validation? Yes? No? Okay, so it is basically what I told you from the sample, how to do sampling in statistics. You have a set of values, you take some random points, and you calculate your measure. And then you go back to your sample, you take another set of points, and you calculate another measure. And in that way, you store many of these measures with different combinations of your data, with different samplings, and you can calculate the distribution. And the thing is that we do that, but we set how many points we want to have in each iteration. So first we are going to have only 3 points. We calculate the p-value, another 3 points, and another p-value. And that's how we got this. Then we move to the next step with a higher or larger data set, and we take 5 points, we calculate the p-value, another 5 points, we calculate the p-value, and we get this distribution. And we do it for many sample sizes. And that's how we get the model of our curve depending on n. Then we fit the exponential function and we evaluate the null hypothesis. This example is the reason why I'm here. So this is actually my work. I do segmentation of protrusions and cells and so on. And we were analyzing how the chemotherapy drug called Taxol was changing the morphology of the cells. So the problem with this is that when you use an automatic method, and you get, for example, the roundness of the nuclei, the more rounded, the less number of protrusions, and hence the less or the lower migration. Okay, the cells don't move and they stay, so the drug is working. And the problem with this is that we analyzed many videos because you have an automatic method that you put it working on and you get the data. And we got these 3 distributions for the 3 different conditions: the control, the cells treated at 1 nanomole Taxol, and the cells treated at 50 nanomole. And when we analyze the p-values, we run a normal statistical test. All the p-values were super low, as Daniela said. Okay, so what we did is we worked on the method, and once we had it, we got these nice scores with the estimation of the p-values, comparing the control group with the 1 nanomole, the control with the 50 nanomole Taxol, and then the cells treated with 1 nanomole Taxol and the cells treated with 50 nanomole Taxol. And we got these nice scores. We got that the value at which we could get a statistical significance when we are comparing this group of cells that are very similar, and actually you can see the roundness of the nuclei is quite similar, is very high, while the other ones are very low, and that we could reject the null hypothesis that they were true when we were comparing any of these 2 curves with this one. So we could say that, yes, Taxol at these doses inhibits cell migration or inhibits cell elongation, and then you can make your conclusions about the biology behind that. Another example is with flow cytometry. So usually, when you do flow cytometry, you get millions of data points, okay, all the cells. So what many researchers do is that they take the medium intensity fluorescence of each of the patient or each of the experiments, and then they just analyze this small set of points, okay? So in this case, for example, they were analyzing whether the use of some corticoids produced eosinophilopenia. They kill the eosinophils of our blood, okay? And this is good because in their case they could see there were differences, but for me it was strange because, okay, you have a set of millions of points and you just take the median, and you don't care about the standard deviation, you don't care about the bias in your data. So we analyzed their data again, and actually what we saw is like if you plot the box plot of all the data, the range of values is actually very wide. If you look at the range of like the standard error of the patient's median fluorescence intensity is wide, but if you take the one with all the data, it's super small. But things look more or less similar. So we applied our method, and we got the same conclusion. So which is nice. Otherwise, it would be a problem. But I mean, the conclusion was made taking into account the entire data rather than just the median values. So let's say that here the data was not that well distributed, there was a lot of noise, and when you take the median values, things look like that. Then these researchers would have been concluding something that is wrong just because they didn't care about the entire data set. And yeah, I think in flow cytometry, for example, is kind of quite useful, this method, because we have always very large data sets. So yeah, glucocorticoids cause an increase of this protein surface expression, and hence it causes the elastinol change. And the last example is quite nice. So these people, they took cells from the skin of patients at different ages, and they wanted to see whether the morphology and the migration of these cells was different depending on the age of the patient. So indeed, they saw that there's some correlation between the age of the patient and the nuclear size. What we did is, okay, let's analyze this data. And we get that we can characterize some measures as the nuclear size or nuclear short axis length with our method. Okay, this is, again, is not perfect as with the normal distributions. Here you can see that the points are not in a straight line. But you can use the decay and the A value to show that there is no difference between, in the nuclear size between patients of 2 years old or 3 years old, as the points are here, the decay is 0, but you can see there's a relationship. So if you do this with your features, where you can analyze this, whether the features you are recording are really telling you some information about the age or about the event you are studying, and then you can introduce them into a model, for example. Also, you can discard those measures that have no relationship at all, okay? Because you can see that the decay in all cases is 0, so that there's no relationship between the orientation of this yellow part and the age of the patient. So you can discard between valid features and non-informative features. But also, if you don't have enough data, as in this case, you can use it to know whether it is worth it or not to keep collecting data. So in this case, there were only around 50, 60 data points, depending on the age. But we could see, actually, that if we analyze the total diffusivity of the cells, like how they expand and they migrate, there is a relationship. So this variable, maybe it is worth it to keep someone annotating this data or using your algorithm. In this case, the data points were very few because they did it manually. And you can really say, okay, this variable is telling me something, so it is worth it to spend more money or to spend more time on that. So after all this, the take-home message is that the discussion is that we can model the p-values as an exponential function that mathematically is very nice because you can derivate, integrate, you can understand what's going on, and you can control everything. That this new difference that we define is constrained, is more stable than the p-value, which is usually employed, and that this new approach enables us to have good practices in the same context as a statistical hypothesis test, and it provides evidences about the existence of this significance in our data analysis. So we can use the software very easily, run it, and see what's going on. And the take-home message, really, this one, is that You can forget everything about today. Really, you can do it. But two things are true. The p-value is a changeable measure that depends on the sample size. Now you cannot forget this, okay? And if you use the p-value as a measure of statistical significance, the conclusions that you are going to do will be unreliable, unrepeatable, and most probably not completely true. So please, this true, take home. I mean, really, like, don't forget them. And we don't have time.
So we have coffee break, but you can do a bit more after,
Yes.
after your coffee break.
So we are going
20,
to,
30 minutes after your coffee break.
okay, so I have the software for you to try. I don't know, any of you brought his or your own data to analyze? Yes, you brought it? Great. Okay, so yeah, there's a software. So what we are going to do is to work on Google Colab, and we are going to install it. We are going to show you how to open it in your drive, not only for this, but also because we are going to use it with Ignacio tomorrow. So we can do it now, and then you will move on faster in the next course. So thank you, and yeah, we can do the break and keep on. Questions? Yes.
In single-cell sequencing, a lot of people use a false discovery rate and report Q values instead of P values corrected for the fact that you have, say, tens of thousands or hundreds of thousands of data points. How does that compare?
In genetics, you mean, right?
Yeah, yeah.
Okay, so that I don't like it, because
Okay.
it is the same. You decrease the confidence interval, you increase your data set,
Yeah.
and you get exactly the measure you want.
But how is the correction itself, the fact that you've said, okay, I expect, because I have this massive sample size, that I have a given rate of some, false discoveries or false positives to correct for the fact that I have a large sample size?
Okay, what I know from genetics is not that you have a huge sample size, but you have a huge list of combinations of groups to compare. So they correct this p-value according to the number of groups you have.
Right, like I'm
so
thinking
they
of.
divide, like let's say that usually you compare it with a threshold of 0.05.
Mm-hmm.
And what they do is like they divide it by the number of groups or whatever, and then they reduce the significance level, and then they need to get like a much lower p-value.
So it's just a sort of brute force, like because I have 100,000 cells, I'm just going to divide my p-value of 0.05 by 100,000 or something like that.
They have multiple groups, so like by chance with multiple groups, you are going to always have a p-value smaller,
right,
because you know that it is possible.
Yeah.
So then they say, okay, I'm going to put a lower level,
yeah,
and then I compare with that.
I'm just curious if, based on this exponential decay, like obviously it wouldn't be exactly the same to just divide that bar that you were sort of counting as some threshold.
No, but you could get the exponential. I mean, you could get the curve,
mm-hmm.
and you could get it for all the groups you have,
mm-hmm.
and you could see if there is a pattern in the
mm-hmm.
curve, for example. Because I can understand that if you have 10,000 curves,
yeah,
you cannot visualize them, and you cannot. But maybe you can cluster them, or you can. Do something with them.
Well, it's not that you would have 10,000 curves, it's that you would have, let's say, 2 groups with each 100,000 data points, because you have so many cells that you're comparing. But I guess my question is, I understand that you can do this, but my question is that false discovery rate calculation, I think, is just like you described, lowering, like the blue bar where you had the like at 0.05 you had your blue bar, and then you had this exponential decay curve that was crossing that boundary. And I'm thinking that this false discovery rate just lowers that bar, right? Because it's just correcting for the fact that you have so many samples. We can talk about it over the break, but I'm curious if you could do a direct comparison of how accurate it is, how comparable it is to your method. I know it wouldn't be exactly the same because it would just be.
False discovery rate, but false discovery rate is related to the power, right, of the statistical test.
My understanding is, that it's just creating a Q value instead of a P value, which is, I think, just a direct division of the P value itself.
Well, I mean,
I don't know if it's
right
direct
now
division.
I don't know. I mean, because I don't know what do you mean exactly with false discovery rate. I mean, if you speak about like the power of the test, like the beta value of a statistical test, then of course you can kind of measure using the deviation of your data. But it's more like, I mean, you could measure it using some randomization. What is your empirical false discovery rate, of course. But it's not about measuring the false discovery rate, but more about characterizing the behavior of your data, as long as you get closer to your true value, like whether it changes or not. So, yeah, I don't know if it answers your question.
No, yeah, I think maybe I'll play around with it and,
Yeah, I mean,
we
we
could
can
just do
check
some
it later.
comparisons. Yeah.
With the paper, maybe it's here. Okay. Yes.
In the case of the experiment of the test that you showed, that you have measured per cell, would you consider, for instance, if you have 100 images of a control case, would you consider all the cells?
Yeah, I'm considering all of them.
And if they come from, if the images come from different, let's say, mice.
I don't know that part of the story.
My question is like independent, you have a control case and a treatment case, can you consider all the cells coming from the control case together, independent if they are coming from different, samples from different animals?
Okay, so if you have samples from different animals,
Yeah.
and you have like you know to which animal belongs each frame for each image or each set of images.
Yeah.
What you can do is to, for example, take the mean value, okay, of all those of the cells of these mice, take the mean value of the other one, and then repeat the analysis, but just taking the mean values of the measures you took by mice or by animal or whatever. I mean, if you think that there is really a correlation or there's a problem of not being independent, you can do that. You can correct for that, taking the mean value, and then repeat the analysis. In this case, it didn't work like that. I mean, it was not that important. But yeah, you could do that, for example. The mean or the median or random samples, for example, 3, 4, 5 from each mice, analyze and then repeat it with 3, 4, 5. Yeah, let's go for the coffee, otherwise they are going to eat all the croissants and so on. Your laptop, go to Drive, and we are going to do this app. So, okay, so this is an empty drive. So we are going to open a Google Colab and then we will try to run the software just for you to open it. So I'm going
We
to.
assume you all have a Gmail account.
Ah, yeah, sorry.
So you have to go
Gmail account.
open your Drive.
If you want all about the Gmail account, maybe your neighbor has a Gmail account and you can follow 2 by 2.
Share the credentials.
Sorry?
If you download, because you're saying this thing about downloading the repository, I mean, is it needed to use Colab?
No, not to use Colab. I mean, in my case, it's for my code. If you want to use it, there's a video. If you want to do it at home and just want to listen. But with Matthew, you are going to use Google Colab to train some networks and so on. So, yeah.
The advantage is that we can do everything in the cloud, so you don't have to store anything in your machine. You only have the data to your Drive, and then you follow the instructions on the notebooks that we're going to show you.
And you have access to GPUs, which is nice. Okay, so
There, good, good, good.
I go to New, and if you have never used Google Colab, we need to install it in our Drive. So we go here, connect with more applications.
Yeah, that's one more, and then one. And then look at Colab, collaboratory.
Okay, you should be able to install it. I'm not able in this account. I don't know why. In Matthew, do you know if this has to do with the student account?
I think for some institutions start adding random extra applications, they have to whitelist them.
But you did it before, right?
I did it with my worker account, but with the student account.
Ah, okay. But you guys are able to?
Are you able to install it?
I have it installed.
No?
How did you get it?
Sorry. Yeah, so I go back.
Yeah. So
This is good to know.
Search collaboratory.
Laura, were you able to use this with your student account?
I can use Colab,
With
but
only one error.
not from within Drive. So you can open a Colab
Yes.
and just run it with your account.
Yeah, install. Yeah, computers.
Yeah, I can manage, yeah.
Just that the student couldn't do that.
But there's a chance.
Oh, yeah, I didn't know.
Like this?
Okay.
And you say that, for example, new. And if I change this,
Yes, collaboratory with one error. As in this.
And you can access your Drive from Colab.
yeah, but you need to import it and so on, right? Yeah, okay, so that we are going to do. Okay, so for those who don't have access to Colab from Google Drive, is there anyone in this situation?
We all install it properly?
You all were able to open it from Google Drive?
Good.
Okay, this is great. So, I'm going to my GitHub account. This one, PMOS, no, that, no? We have it in the slides. Okay. And here are the instructions. So, in general, Google Colab is very easy. You just write codes and you enter, you click on enter and it runs. So the way Colab works is like somehow like a Linux, right? Like in the way you install things, and like a Python notebook. And you don't break your machine.
You go to your GitHub account.
Do you have the slides? Otherwise, you can just copy PMOS and this part, and it should appear on Google.
It's on the course GitHub also,
Yeah.
under your name. The link.
Yeah. In the,
So you're gonna be copy pasting the code from there.
yes,
to Colab.
but I can write it as well. Yeah, but I'm going to copy paste. Just until I clone the repo because there's a notebook inside. I mean, actually, because from Drive it's different, but from here, I'm going to try one thing, okay? And we do this.
Now it's just like an app.
Okay, so this is great. So, okay, from the beginning, we have an empty column, right? So you can go to the repo, and in examples, this is everything on that. We have here, we are going to use nuclear morphology.
So is it right there?
Are you here?
So when GitHub, on there is other examples. Okay?
So is that third line wrong? The disk analysis, is that meant to be the PMOS?
Yes, we will change because it is done also to run it on your laptop and so on. But yeah, this is wrong. Thank you. So now in a blank Google Colab notebook, we can go to archivo. Sorry, file. Sorry, file. Open notebook. And then here we can open it from many sources. So with Ignacio, you are going to open it from your drive, but now we are going to open it from GitHub directly. So here we just need to give the URL. So we go here, we copy it, go here, we paste it, we say look for it, and it opens it automatically.
Thanks.
And now you can change it to whatever you want. It won't change my record, so you can play with it. And this we can change. Oh, sorry, sorry, your name was Adam. Okay. Okay. So the thing is that now we have a blank notebook. The notebook doesn't know anything about our Google Drive or whatever. So what we are going is to give all the data we need here. And for that, we say new code here. Yeah. Ah, they are still opening the notebook. Okay, sorry.
You actually just give the PMOS just the GitHub open, you'll find both the notebooks. If you actually just give the link of your whole GitHub, you'll find both notebooks.
Yeah, and it open both.
And it will show both. You enter the click search, and then it shows both notebooks there.
Okay. I mean, you have many ways of it. Yeah, nuclear monitoring. This one, sorry. This one. So the instructions are here to GitHub. You can tell where is your drive and give access to your drive to run your code using the data you already have in the drive and so on. In this case, I think we won't need it, okay? Is it the first time you've used Notebook? Is anyone who has used Google Colab before? 4. Okay, so you can help us.
As much as you can.
Okay. So what we are going to do now is to tell to Google to clone our repository. Okay, to tell Google to take all the functions and all the code that I have on my GitHub to move it to the Google running session by just doing git clone as you would do it in Linux, for example. So add a code line. I will copy paste here.
This is the GitHub page.
Okay. I changed it. You can change whatever. can change, and if it won't change anything, you can change, remove it, load it again, and nothing will crash, which is amazing. I mean, no, but it's true, it's really nice.
Right, change the code to make apps.
But you can upload it again. Yeah? Okay. So I'm going to clone my repository, which means that I'm going to make a copy of everything in GitHub in this session of today. Now, it appears here. If you click on this folder, and everything is here, in the cloud. This is wrong, sorry. Need to change it. Okay, did you clone the?
You can make it the font larger so you can use it. Yeah.
No, just I mean like.
This is not you can copy from yeah. And go down. So that way you copy the library method that she has into your
Okay, so I changed this. Okay, I commented by adding a hash here and wrote PMOS because it's the name of the folder where our themes are. Okay. So actually, well, here, if you go down, the good thing of Colab is that you can work on it, you can run everything, and provide the notebook, like already run, so you can show the results you got, and you can give it to a colleague or a collaborator, whatever. So here in my Colab, even if we are going to run it again, you can see the outputs of the cross-validation and the plots that are similar to the ones in the paper. Okay. And the lines and so on. So now that we have cloned the repository, here we tell the path where all this is, and we can run it, and it will work. Yeah, sorry. Yeah, so we go back to this version. So, okay. So before running any code, we need to install all the requirements we need. So if you are going to do this at home, follow the instructions. Okay. There's a video as well that you can watch at it in YouTube. You can stop it and you can see how to do everything with your own data or using Google Colab. Okay. So we copy this. We add here a new code line. We paste it. And what we are telling to Google is to install all the requirements listed here. So the path that I write here, you can get it very easily. If you go to the file you want to run, you click on the right button, and you say copy the path. Whenever you are in any kind of file, copy, and paste it here. And well, it is the same. Okay. So we run it. And it will start downloading all the things you need. Usually, when you take a Python repository in GitHub, they should always have this file, this requirements file, that you should run as this, or with an exclamation mark if you are in your local computer, just to get all the libraries with the right version you need for your code and so on. So this is quite important. And if you are publishing a code, you should always provide this txt file version here. It looks like that. Okay? You can create it with Conda. So it has downloaded everything. And now we can run this part that was giving us some errors.
I remember the path.
I was ready to move.
Okay, so most of the functions that we are going to use are here in this folder. So I copy the path and I put it here because I need to tell where is my functions here. Okay, and we can run it. Is it working for you? Did you run it? Yeah? Okay, so now the column identifying the rule must have the main condition and should be the first column. So maybe I can show you this.
Can you go back to the path that you changed?
Yes.
Yes, please.
Yeah. So
Ah,
last content. Consent and emotion.
So the data we are going to analyze in an Excel file or whatever, it has to be ordered like that. Like where is your condition and the name of your conditions, and then the variables. Okay, area, short access length, or whatever. Okay, it should be like columns like that. In a CSV.
Some people were still changing the path, so you can repeat it just the CSV file.
So, once we have cloned the repository, we have inside the requirements for the code that are in this folder, must here requirements. Okay, so we say, okay, Python install my requirements, and we click and it installs them. Then the next thing we have is this one. So here I need to tell the path where my code is. If I have in my drive, this will change. It will be something like my drive experiment one, whatever, where I have the code. Okay. So this one, if you follow these steps, you shouldn't need to change it except this one. But if you have the code downloaded in your drive or whatever, just make sure that you tell Python where you have your functions. Okay, so we run it. Did it run now, all of you?
What file did you get that code from?
Sorry?
That code.
Which code?
That code?
This?
Yeah. What file is that?
Is the first line of the notebook? No. What do you mean?
Okay. Yes.
I think you
Yeah,
have to open.
Where did I get it?
Yeah, what file is that?
What type?
What file?
Ah, what file? Ah,
Yeah.
sorry, sorry. It's nuclear morphology. Okay, it's written here. Here, this one, and in GitHub, these examples, this one. Nuclear morphology.
Can I ask a question about Google Colab? So we've cloned this repository, and if I were to close my browser right now, it would disappear. Like I would do it again each time I opened up a session. And I'm editing this notebook, which exists on your GitHub,
But
which
you
of
want
course.
to have your own notebook, right?
Sorry.
Okay, sorry.
I'm just wondering if so I open it up and I'm saving it to my drive, let's say, and then I can save my changes. But if I don't do that, then similarly, if I close the browser, everything is gone.
Yes.
And is there a way that I can, like, I would just use the normal git commands to say like fork the repository and save my own edits to my own GitHub? I could do that. If I wanted to, instead of saving all my changes that I made to my drive, if I wanted to just update a local repository and.
There's a way, but it's a bit complicated.
Okay.
I can tell you later.
Okay. Yeah.
Yeah. So you can clone your repository in your Google Drive.
Yeah.
And keep it with the Git, and then do any change you want and push to your local repository. You can do it, but it's a bit complicated.
But it would be, is it just the same as if I cloned it to my to my local computer? It is different. Okay.
No. Okay.
You can show me. I was just curious if that's something you can do.
All of you later, or
can you not just use normal git commands?
That's what I'm wondering if you.
Yeah. If you have a fork, I think you can just do add and commit push.
Okay.
Yes, but if you close your session, I mean, if you are in the same session, you can do it. But if you're close, you leave it there and you want to keep on working next day. You don't want to clone your repository again and do the push again and so on. There's a way to have it in your drive connected to it, as if it was your local computer, your local machine.
Okay, so that as you're updating, it's saving to your drive, and then when you're ready, you just push the change.
So did you manage to open the notebook?
No, I can open it. I can find it.
Yeah, because I can repeat it. I mean, the rest is just to run the code. So this part, we will take the time to read.
No, it doesn't find it.
So it's here.
Yeah.
Oh.
No. So, now here we need to write a path to the data. Data, we are going to use morphology. Is this one? So actually, here maybe I should write just in case. Content. No, we need to use. So, copy the root, the path.
Is it R before the sum?
No.
Yeah.
Yeah, because you can remove it. You always put it.
What does that mean?
To read like a text, to not have problems with the spaces and the script characters and so on. But
Okay.
I always do it like that.
Okay, I didn't know.
But yeah, I mean, it's just a thing. Okay. That's it.
Just let me hear.
Yeah, okay, that's it. Okay, so now we say where is the data and which is the file we want to analyze. It can be the CSV or the XLS or whatever. Here we say until which end we want to calculate all the p-values. What is the minimum sample size for which we want to start our calculations? This one it can be 3, 4, whatever, and this one can be 2,000, but from 1,200 is almost enough. And the grid size is how many data points I want in my cross-validation for each of the distributions at each of the data sizes. So we want all these parameters, they are explained in the paper in the supplementary material and so on. And also here. We also say the kind of test we want to apply. Usually I would use this one because the data sometimes is normal, but most of the time it's not, at least in my case. This is the gamma I told you. This is a recommended value that is also in the paper. The running and the one, the code. And it takes some time, so I mean, yeah, we're not to wait all the time here, but it takes quite a long. So we can see the first iteration and then it runs. So now it takes the group of 2 years old patients and it's comparing it with the 3 years old, and it's going to start doing the cross validation for all the n values and all the faults. Okay, we are taking it, and you can see that it will keep running.
Yeah. Everybody gets an error there. From the bus.
Okay, did you change this path here? You all have this path?
No.
Yeah. The path to the data?
Okay.
Did you manage to run it? Yes? Who didn't? That I can help you? Now you can run any GitHub code. Right? No? Because changing is that this intensity is yeah, it doesn't matter. So
Yeah, but I think given zeros and that we want
okay, so let me see. So
It work now?
okay, so for the path here, don't miss this line here, okay? Because we need to give the path to the entire folder. Control 5. Is it working now? No? And? No. Now this is just like so we can move to the
Explain a bit the data that we are.
The data, yeah. So, okay. So here are all the, like, we are calculating the distribution of the p-value for each of the sample sizes, right? And at the end, when it finishes, what we store them, just to have them and if we want to use it for plotting or whatever. And here is not, yeah. So one of the things you get is this table. So it's giving for each of the comparisons the value of a in the exponential function, the decay c, the estimated minimum data size to get a statistical significance, the n alpha, okay, the estimated one and the theoretical one. Because you can get the estimated one from the data, so you analyze when the whole distribution of the p-value is smaller than alpha, or you can use the exponential function and just solve the equation. And this is whether you reject the null hypothesis or not. So this is the decision. And all these 5 values for all the features you have in your data. So these are numbers, and then here are the plots from the plots I show you, and the ones that are in the paper, with A and C, so with the decay. And here is the N alpha. Okay, so what is the minimum sample size to get the statistical significance for each of the comparisons? And here are the chords. Of course, for some data sets, we didn't have more than 500 values, but still we can see, okay, we can fix this exponential function. This is like the mean values of the estimations we did and the exponential approximations. Yeah, for all the comparisons, and actually you can see that even if the data size is not very big, you can kind of intuitively you can see how it's going to be your core. And this is for orientation, which was not informative at all. I mean, I see this one is not telling us anything about the age of the patient. And these are the so the distribution of your data. I don't know if you see anything. And like the distribution, so you can see whether the results make sense or not. But here there's a lot of data and groups, so we don't really see too much. Here is the orientation. You can see that it is the same. This is the orientation of the cell nuclei. So actually, it is completely uniform. There's not any pattern for any age, and that's why our data looks like that. And yeah, and that's it. So actually you can save your image as a PNG, or you can give here a path in these functions to save the image as a vectorized graph or whatever. You can go to the functions and manipulate the plots. The plots are quite easy to get. Yeah. So you should get all these once the process has finished.
So in the first column it says condition. In this experiment would be the age of the patient?
Exactly. So condition is like the groups we have. It can be group 1, group 1, group 1, and the data for group 1, group 2 actually. Maybe I can show you. So this is a CSV file that you can see the columns. Okay, so the first column has to be always condition, and then your different variables and their values. Just make sure that this is a dot, okay, for Python, and that you wrote it as a semicolon here. If you use a CSV, if you use Excel, it's fine. But these kind of things, the dot and the commas, please make sure that they are fixed with the Python configuration. Okay. Any questions so far? Okay.
Yeah, in terms of time, it's time to stop.
Okay. Yeah, we are done.
You're done.
Yeah.
Is there any questions? Anything that's here? Yeah. But what's false? Then how big you n equal something and false equal
What?
yeah. False.
False. False. Is the number of iterations you run for each n value. So is the number of iteration in your cross validation, in your Monte Carlo cross validation.
How many different groups you create to do the cross validation? That's officially called fold. You do 10 fold cross validation, you create 10 different groups.
So these are the parameters. So this is the way you do it, right? You have in general in Monte Carlo cross validation, you have your two data sets, and you choose a random number of blue points in the red one and no green points in the blue one, and you choose 20 of them. You compare them, and you say the p-value. Then you take them back with replacement, and you take another ones, and you repeat this false number of times, okay? And you get the list of p-values. Then you change the n value, you increase it, and you repeat this again for 150, for whatever the number puts in the sample, and you keep doing it, increasing the n size. And at the end, you get a list of p-values for each of the n sizes you choose, and you try to fit the exponential function. I mean, here you will have p-values and n, and then you just will fit. And you can do it anywhere, R, MATLAB. It's like, yeah.
Do you make sure that the samples on each fold are different? That you don't repeat or you do repetition?
No. So actually, that's scaffolds. I mean, well, it's not scaffolds, but it's more in that sense. So in Monte Carlo, what you do is you randomly choose samples, but you make sure that you make so many iterations as to cover the entire data set, even if you repeat it or not. Depending on the experiment, if it doesn't have sense to do replacement, like you can throw these ones out and then take another ones until you cover the entire sample. But here, no, you don't need it.
And it almost has to work
This approach,
process.
when you combine the samples, do you wonder if they be like potential
It was still happening on that.
if the sample are versus
Yeah.
so different or
Okay.
You choose them randomly, completely. So the thing is that you repeat this process for
yeah, I mean like, are they independent or not?
the sample.
I mean, no, I mean like the, yeah, imagine like you have, maybe I'm confused. Yeah, the way like you are taking the samples.
The way you choose each of those blue points or the green ones is completely random. So this, some of you asked me like, okay, if you have like different experiments that they might be correlated, it is true that maybe what you should do first is to average for each of the experiment we have, so you can remove this dependency, and then instead of put all the points in the data set one will be your averages. You could do that for independency. No? Okay. Yes?
So we can add more data sets and then run it or compare more than two.
Yeah, so that's actually what you are doing in this example. So there are 9 conditions, I think, but it always makes the comparison 2 and 2 and 2 and 2, okay? So it doesn't give you like a ANOVA test that it compares all together, but it takes data set 1, data set 2, and it compares them. Then data set 1 and 3, it compares them. Yeah. Of course, then it doesn't make like data set 2 and 1. I mean, it has already been done. But yeah, you can have many conditions. Yes?
So what if your random number generator is failing?
Then you create a random number generator.
You track always the same data.
Okay, so
Can you understand if something is wrong?
I mean, so in this case, I took Python's random generator. I mean, if your random generator is wrong, you put it right. No, you correct for it. If they are always the same, I mean, what you will get is no distribution for each. I mean, the p-value will be always the same if you are comparing all the time the same data sets. No? These values, if the randomization is wrong, they will be the same.
Okay.
So you will see that their distribution is actually the same all the time. Right and wrong. More questions?
I will make a pause and then.
Yeah. So 5-minute break. If anyone has problems to install Python, following the recommendation from Ariana, please ask Ignacio STI. And then we will move to the plotting with Python session. It's going to be done remotely by Ariana. She's still in Switzerland. And so she will be with us by Skype, and Esteban, Ignacio, and I will be in the room to help you with those problems or questions. So yeah, take 5 minutes break to refresh all the statistics. And thank you, Esteban, for this great work.
Thank you.
Especially on
Session?
Yes.
And well, yeah, 5 minutes break and then I am online. Okay.